All right, chemists, so let's continue on our discussion of acids and bases, and now let's talk about the pH scale. So you might have heard about the pH scale, you might have heard like pH neutral, water is neutral. So pH is a way for us to quantify the amount of acid in a solution, in a substance. And so there's lots of ways we can measure pH. There are different types of indicators can use. We can use a pH meter to just measure the pH, and it'll spit out a number. So that's what this meter is detecting. The concentration of hydronium ions in this solution. You can also use strips. You might have seen pH paper strips that look like this, and they turn different colors depending on what pH there is. And so there's like a reference chart here to tell you, okay, if you have basic solutions, that you'll see these dark, like blue green colors. If it's more acidic, then you'll see these orange, red, yellow colors. There are also natural indicators. So red cabbage is actually a natural indicator. There are different colored substances within red cabbage that turn different colors depending on what type of acidic or basic environment that substance is in. So those are some other types of indicators to determine whether a substance is basic or acidic or neutral. All right, so pH, what does that P mean? So, like I said, indicators can tell us if a solution is an acid or a base. So, kind of the relative amount of acid, hydronium ion, excuse me, versus hydroxide anion. So, in lab, when we use a pH meter that looks like this device is saying it's spitting out a number of a pH of 4.00. We can also we measure hydronium ion by determining the pH of the solution. So we're measuring hydronium or the hydrogen cation. So that's why there's this H there, pH. So it's like P of H concentration. So what pH means, this P means you take the negative log of the concentration of hydronium or H plus, but we know that in solution H plus exists as hydronium. So this is a concentration of hydronium in molarity. We want to make sure that that concentration is in molarity. So that P that comes before the H part of pH, P just means negative log of anything. So if I had P, oranges, so oranges, that means that, oh, I spelled that wrong, oranges, oh my gosh, oranges, then P oranges would mean that you take the negative log of the concentration of oranges. And this is important because we can calculate or determine the pH of a solution, H meaning concentration of hydrogen or acid or hydronium. We can also calculate the pOH of a solution. All right, and pOH is, right, we just take the P part, meaning negative log, and so pOH is negative log of the concentration of hydroxide anion. So that's pOH. All right, so for water, the pH, so we know that hydronium, that concentration in pure water is, that concentration is 1 times 10 to the negative 7 molarity, right? And that is also equal to the hydroxide concentration, right? This comes from our Kw expression. That is the concentration of hydronium times the concentration of hydroxide. And in a neutral solution, those two values are equal to one another. All right, and since Kw equals 1 times 10 to the negative 14, that means each of these variables equals 1 times 10 to the negative 7. So this is where we get water. Water is neutral. Water is pH 7. Because when we put the 1 times 10 to the negative 7 into our pH equation, so take the negative log of, so this is log base 10. I'll keep that in mind. Log base 10. 1.0 times 10 to the negative 7 is our concentration of hydronium. This equals 7.00. So I'll just show you putting that into a calculator. Can I show this here? So our log button is right here. Okay. Here's my log button on this calculator. So if I type this in to calculate pH, it would be negative log, all right, 1.0 e to the negative 7. So this is what I put into my calculator. I want you to be able to see everything. Right? So there it is in my calculator. Ooh, can you see it? So negative log parentheses 1.0 e to the negative 7. All right, and if I stick that into my calculator, you see that it spits out a pH of 7. But remember, calculators don't understand sig figs. So how are sig figs applied to logarithms? So the significance in a pH value, so after you take the logarithm, is only in the decimal places. All right, so this first number, the integer number, like 1, pH 1, 2, 3, 4, those whole numbers, this is only telling you the exponent, essentially, right? The exponent from the 10 to the negative 7. So we know 10 to the negative 7 doesn't contribute to significant figures. So same thing here, that this 7 does not contribute to the significant figures. So what do I have here? Significant figures in logarithms. So the significance is only in the mantissa, or essentially the decimal places. All right, so the number of significant figures in the concentration value that you put into our pH equation becomes the number of decimal places in your pH value. So you see here in our example, we have 2 significant figures in our molarity. So we have, in our answer, we need to have 2 decimal places. 2 decimal places. So, I could write this a bunch of ways. So for example, for water, if I wrote our molarity of hydronium was 1 times 10 to the negative 7 molarity, all right, if you stick that into your calculator, you get 7, but we want to make sure that we show the correct number of significant figures. So since 1 times 10 to the negative 7 has 1 sig fig, that means our pH needs to have 1 decimal place. So our answer would be 7.0. So 1 sig fig becomes 1 decimal place in our pH value. And so, let's do another example. Instead of 2 sig figs, since we already did that, let's do 3 sig figs. So if our molarity has 3 sig figs, so 1.00 times 10 to the negative 7 molarity. So since there's 3 sig figs here, our pH would actually be 7.000. And so this translates to 3 decimal places. In our pH value. So those are the rules for logarithms. It's not just for pH. It's if you in a equation use a logarithm or a natural log, these rules still apply. That the number of sig figs that you put into the logarithm, when you spit out a number, it's the number of decimal places is where the significant figures go. All right. And so with pH, so remember, neutral water is our reference point. That's our middle ground. We call pH 7 neutral. That's where hydronium is equal to the concentration of hydroxide. So neutral pH is 7. So any substance where we have a large amount of hydronium, so acids, will have a pH between 0 and 6, so less than 7. While bases, on the other hand, have a smaller amount of hydronium, or hydroxide, so the pH will actually be larger than 7, so between 8 and 14. So yeah, less than 7, acidic substances, more than 7, basic substances. So here's an example of different substances on our pH scale. So you see our reference point, water, pure water is 7. All right, so pH just tells us the acidity of the solution. pH also tells us the amount of hydronium present in the solution. So some acidic substances, battery acid is quite a strong acids, hydrochloric acid that's in our stomach, lemon juice, grapefruit juice, lots of things that we eat on a daily basis are acidic. So some basic substances, seawater is slightly basic, baking soda, the Great Salt Lakes, because of all that salt there, is quite more basic than pure water. Ammonia, soap, bleach, drain cleaner, those are basic substances. All right, and so I kind of told you about, gave you a glimpse into POH, but we know that pH for pure water is 7. right? So HPH, meaning concentration of hydrogen cation or hydronium, but we know that in pure water we have hydronium cation and hydroxide anion, so we can calculate the pOH. So this tells us the concentration of hydroxide in a solution. All right, so we take the P expression. P just means negative log of anything, so pOH means negative log of hydroxide concentration. All right, and so we know in neutral water and pure water, hydroxide concentration equals 1 times 1.0 times 10 to the negative 7 molarity, because those concentrations of hydronium and hydroxide are the same. So pOH for pure water will also be 7.0, how many sig figs? 2. 7.00 pH. And pH doesn't have a unit. You just say like pH equals 7.00. All right? And so what you see here is that for any solution, pH plus pOH will always equal 14. It'll always equal 14. So that's why our pH scale is between 0 and 14. So the question is, why does it always equal 14? So this has to do with our Kw expression. All right. So since I told you pH plus pOH always equals 14, that means as long as I know one of the concentrations of hydronium or hydroxide, we can calculate the concentration of the other using this formula, because we know Kw equals concentration of hydronium times concentration of hydroxide. This always equals 1.0 times 10 to the negative 14. So essentially, if we take the negative log of the entire thing, all right, so how logarithms work is essentially we break this up, that we take the negative log of hydronium to give us pH, and then you add that to the negative log of hydroxide to give pOH. This will always equal 14, because the negative log of 1.0 times 10 to the negative 14 is 14.00. So pH plus pOH is always equal to 14.00. So as long as you know one of the species, the concentration of one of the species for a solution, you can calculate the other concentration using that formula. All right, and so yeah, that's what I have here. So you can either be given the concentration or the pH or pOH, because that can always be, you can always take the anti-log to go from pH to pOH. And actually, I'll say that. So if we want to go from pH to hydronium concentration, right? If I give you a pH, like pH 8 or something, right? You actually have to take the anti-log. So the anti-log is just 10 to the n. All right. So let's say if I have a pH of 8, to get hydronium concentration, you take 10 to the negative pH, and that will give you hydronium concentration. Right? Or pOH. So if I give you a pOH value, so 10 to the negative pOH for a value will give you the concentration of hydroxide. So this is how you take the anti-log. I also think anti-log is on your calculator as well. All right, it's like the second. So on this calculator, you see we have our log base 10 number, and the if you take the do shift on that same button, the shift value is 10 to the. So that's essentially your anti-logarithm. All right, so this is important here. All right, how to undo your pH and pOH. All right, so let's identify these different solutions as acidic, basic, or neutral. So remember, neutral is 7, a pH of 7. Basic is anything above 7. Above 7. So anything above 7. Acidic is anything less than 7. All right, so HCl with a pH of 1.5. 1.5 is less than 7, so that's going to be acidic. Pancreatic fluid, so it's not giving us a pH, but it's giving us a hydronium concentration. So 1 times 10 to the negative 8 molarity. So if you just calculate the pH of that value, this is giving us a pH of 8.0. So 8.0 is larger than 7, so this is actually basic. All right, a soft drink has a pH of 3.0, so this is less than 7. All right, so those are less than 7. This is more than 7. So a soft drink is acidic. All right, pH of exactly 7.0, that's basic. Or sorry, that's neutral. Huh. So now this one's different. This has an OH concentration, a hydroxide concentration of 3 times 10 to the negative 10. So we can calculate the POH here. So POH, if you stick that into your calculator, if you take the negative log of 3 times 10 to the negative 10, this gives you a POH of 9.5. All right, and so remember, pH plus POH always equals 14. So that means our pH for this, if you do 14 minus 9.5, our pH is 4.5. So since pH is 4.5, right, that's how we determine if something is acidic, basic, or neutral. It's from our pH value. Since this is less than 7, this would be acidic. And finally, it gives a hydronium concentration, so 5 times 10 to the negative 12. So let's just take the negative log of that to get a pH. So pH equals 11.3. All right, and so 11.3 is greater than 7, so this is basic. Okay, so let's do a little bit more practice doing logarithms. So we have a hydronium concentration in wine is 5.0 times 10 to the negative 5 molarity. This is our H plus concentration. What is the pH of wine? So remember, here's our equation for pH. We do negative log times negative log of the hydronium concentration, and so they straight up give that number to us. So we just stick that into our calculator. So negative log of 5.0 times 10 to the negative 5 molarity. That's our H plus, it gives it to us. It is 4.30. So wine is acidic. Cool. And let's take a look at sig figs here. Since molarity has 2 sig figs in molarity, we need 2 decimals in our pH. And so this is the correct answer. pH is 4.30. So it looks like it gained sig figs, but remember the whole number here out front does not contribute to sig figs for logarithms. All right, so here's another one. The OH concentration in household bleach is 1.99 times 10 to the negative 2 molarity. So this is hydroxide concentration. What is the pH of bleach? So there's a few ways you can do this. I like to just, since they gave us OH concentration, let's just calculate POH. So POH equals negative log of OH concentration, and they give it to us. All right, so we're going to stick that number into our logarithm. So negative log of 1.99 times 10 to the negative 2 molarity gives us a POH of 1.701. And I'll note here with sig figs, since there's 3 sig figs within molarity, we need 3 decimal places in our POH. All right, so that's our POH. And our other equation to remember here is that pH plus POH is always equal to 14. So pH, right, pH plus POH equals 14.00. So we'll just stick that number in POH. And then so if you do 14 minus 1.701, you get 12.299. That is our pH. All right. And there's also another way we can do this, so maybe I'll just kind of write this on the side. So this is an alternative way. So since they give us OH concentration is 1.99 times 10 to the negative 2, we can also use the Kw expression. And the Kw expression is essentially, this expression, but you take the log of it. So Kw, which we know is 1.0 times 10 to the negative 14, that equals H plus concentration, H3O plus, times hydroxide concentration. Since we know that number, we can just calculate for H3O plus concentration directly. So H3O plus concentration, our acid concentration, is 1.0 times 10 to the negative 14 over 1.99 times 10 to the negative 2. All right, and that will give you an H plus concentration. I actually didn't do this. E negative 14 divided by 1.9 e to the negative 2. So H plus concentration is 5.025 times 10 to the negative 13 molarity. And then you can take this number and plug that into pH. So pH is equal to negative log hydronium ion concentration, so negative log of 5.025 times 10 to the negative 13. So negative log of that number gives you 12.299. See? It's the same number. All right, so that's another way you can do it. All right, or you can just calculate POH and then plug it into this equation to calculate the other one. So there's lots of different ways you can do it. All right, so this next one, pH of a solution is 3.75. What are the hydronium concentration and hydroxide concentration? All right, again, there's a lot of ways to do this. So we want concentration of both. So if pH equals 3.75, that means that the concentration of hydronium is equal to the 10 to the negative pH. So that means we do 10 to the negative 3.75. And that will give us hydronium concentration. Also remember, pH plus POH always equals 14.00. So that means POH equals, 14 minus that number. Do I have it here? POH equals 10.25. And so we do the same thing. All we have to do is undo that logarithm. So our hydroxide concentration is equal to 10 to the negative POH. So it'll be, what you'll put in your calculator is 10 to the negative 10.25. All right. And so those are our two concentrations. Right? This is what I mean by, as long as you know one of the concentrations of hydronium or hydroxide or one of the pHs or POHs, you can calculate the other one. And so our answers here, and I'll remind you of sig figs. So in pH, remember it's only the decimal places that hold significance. So each of these values only have 2 sig figs. So our molarity should have 2 sig figs. All right, and so if you stick this in your calculator, you should get 1.8 times 10 to the negative 4 molarity for, this is for hydronium. And then the other one, 10 to the negative 10.25, that is 5.6 times 10 to the negative 11 molarity for hydroxide. All right. And a way to check this, all right, to make sure that it's right, if you actually multiply both of these two numbers together, you should get 1 times 10 to the negative 14. So there's also other ways you can do this problem. So Kw equals H3O plus times hydroxide. All right, and so if you multiply those two numbers together, 1.8 times 10 to the negative 14 molarity times 5.6 times 10 to the negative 11 molarity, this should equal 1.0 times 10 to the negative 14. And I'll just check it right here. Why not? So 1.8 e, not negative 14. Whoops, negative 4. Negative 4 times 5.6 e to the negative 11. Yep, and I get, so when I do that in my calculator, I get 1.008 times 10 to the negative 14. So essentially 1 times 10 to the negative 14 with a little bit of rounding at the end. So this next slide is actually the same question, but I decided to make it an extra credit assignment for the final. So for this question, it's the same as the previous, but I'm just going to change the number. All right, so if you send me your work for this, I will give you extra credit on the final. So let's say we have a pH of a solution that is, I don't know, 5.25. So if we have a pH of a solution that is 5.25, tell me what the H plus hydronium concentration is and hydroxide concentration is, and I will give you extra credit. So just email me, all right, the work for this. And so it's exactly the same as this previous question, except just with a different pH value. And so you'll calculate a different POH value. All right, so show me the work for this slide with a pH of 5.25. Tell me what the hydronium concentration is and the hydroxide concentration is at pH 5.25, and I will give you extra credit on the final. All right, so how many more learning checks are we doing? 2 more. Okay, so we have a pH of a cleaning solution that is 13.5. What is the hydroxide concentration? All right, this one's a little bit easier than the other one. So we want OH concentration. So if we can get POH, then we can easily undo that logarithm to get OH concentration. Thankfully, they give us pH. It's 13.5. So if pH equals 13.50, that means POH has to equal, 14 minus that, 0.50, because those have to add up to 14.00, right? With that one equation. So since we know POH, we can easily undo that to get our logarithm, or undo the logarithm to get hydroxide concentration. So if POH equals 0.50, that means hydroxide concentration is the antilog of POH. So it's 10 to the negative POH. And so 10 to the negative 0.50. All right, and so you see here for sig fig values, there's 2 sig figs here in our pH, or sorry, there's 2 decimal places in our pH, so there should be 2 sig figs in our answer. So hydronium concentration will be 0.32 molarity, right? For hydroxide concentration. All right. Okay, so now this last one. Okay, so what are the pH and POH of coffee if the hydronium concentration in coffee is 1 times 10 to the negative 5? So since they give us hydronium concentration, we could easily turn that into pH. So the pH of coffee is negative log of our hydronium concentration, so 1 times 10 to the negative 5 molarity. So the pH in coffee is 5.0. Since there's 1 sig fig in our molarity, there should be 1 decimal place in our pH. All right, so we have the pH. So we can easily get the POH, right? POH is just equal to 14 minus pH, okay, that we just calculated. So POH is just the difference. So what, 14 minus 5 is 9.0. All right, so which one's that? Number 3. Great. So essentially how I approach this question, they're asking for pH and POH of coffee. We know that those will always add up to 14. Since they give us hydronium concentration in coffee, we just turn hydronium concentration into pH using our negative log expression. Then once we have pH, we can back calculate to get POH since they always add up to 14. And so you get pH is 5.0, POH is 9.0. All right, so let's move on to neutralization reactions. So neutralization reactions occur between acids and bases. We know when we mix acids and bases that they cancel each other's effects. So like, when you have an upset stomach, it's too acidic in there, you take some Tums, which is slightly basic, and it neutralizes all the acids in your stomach. So a neutralization reaction is just a special type of double displacement reaction where it's between an acid and a base. And the products are water and some form of a salt. So for example here, this neutralization reaction is between HCl, which is our acid, because it has a proton there. We have our base, which is sodium hydroxide. Right, bases, so in this case has a hydroxide right on it. And so you see when we do our switching partners thing that we do with double displacement reactions, you see one of the products is HOH, which is water, so H2O liquid, so that's one of our products, water, and then the other one is some form of a salt. So in this case, it's sodium chloride, so that's our other product, sodium chloride aqueous. Here is our salt and water. It's not always sodium chloride. It depends on what the acid and base are. All right. And so with acids and bases, we will talk about titrations. Although we're not doing a titration in lab, in our in-person lab, you will see a titration within your digital labs. So with acids and bases, we talked about indicators and how indicators change color depending if they're in an acidic environment or a basic environment. So indicators help us with titrations to know when our solution is neutralized. So with indicators, some of the indicators we use are litmus paper. All right, and so there's two types of litmus paper. There's blue litmus paper and red litmus paper, and you dip both of those in your solution, and depending on what color they change will tell you if that solution is basic or neutral, or acidic. Also, we have universal indicators. Those are more accurate. They'll change color depending on if they're in a basic or acidic environment. But in lab, typically we use phenolphthalein, which turns pink in a basic environment. So if you start with an acid and you start adding base, all right, eventually it will become neutral or it will no longer be acidic anymore. So once it becomes neutralized, your phenolphthalein will turn pink. But if phenolphthalein is in an acidic environment, it will be colorless. All right. So with acid-base titration, so what is a titration? A titration is reacting an acid and a base together, but in a quantified way. So you add a known amount of base to an unknown amount of acid. Or it could be the other way. You could add an unknown concentration of acid, you could add a known concentration of acid to an unknown amount of base. So a titration is important. It's a way to quantify a neutralization reaction. So using the indicators that I discussed in the previous slide, we can determine when the endpoint or when we've neutralized our reaction. So what's important here, what I mean by neutralized, when we become neutralized, the concentration of hydroxide is equal to the concentration of hydronium in our solution, meaning that the moles of hydroxide are equal to the moles of hydronium. So this is the important thing. Moles of hydroxide equal moles of hydronium. That every acid particle got neutralized by a hydroxide particle to make water. And so this is important. This point is important because we can use this knowledge where at neutralization, moles of OH equal moles of H3O plus, to use this in stoichiometry to figure out the concentration of the unknown species. All right. So neutralization is just neutralization occurs in titration problems. So when we react an acid and a base to form salt and water, that's essentially we're neutralizing the base and the acid to form salt and water. So once we're neutralized, our OH number of moles equals our hydronium number of moles. All right. So if we look at this example, so this is another neutralization reaction. So ammonium hydroxide, this is our base. HNO3, this is our acid because there's a H there. And you see that we form salt in the form of ammonium nitrate and water. So this is just another neutralization reaction. So let me show you what I mean by neutralization. So if we write the total ionic equation here, all right, so we remember this from, previous lectures, we separate all of our cations and anions. So NH4, this is a cation, so that's aqueous, plus OH minus, there's our aqueous, plus H plus, that's our cation, aqueous, and our anion for HNO3 nitric acid is NO3 minus, aqueous, arrow. So all those are aqueous, so we split those apart. And then we also split apart our salt here because it is also aqueous. If you check the solubility chart, so NH4 plus aqueous plus nitrate aqueous. Thankfully, there's just one of each. We don't have to worry about coefficients. And then finally, water. So water is a liquid, so it does not split up. Not split, so we just keep water as is, H2O liquid. All right, so there's our total ionic equation. But let's figure out the net ionic equation to see, what is the important reaction going on. So let's identify our spectator ions. So if I look, there's NH4 on our reactant side and NH4 on our product side, they're exactly the same. There's a spectator. So OH on our reactant side, I don't see OH exactly as written as our reactant on our product side. It's actually tied up in water. So OH is not a spectator ion. H plus is also now tied up in our water product, and so the only other spectator ion is nitrate, NO3 minus. That is also a spectator because it looks exactly the same on the reactant side and the product side. So our net ionic equation will be just rewriting the equation without those spectator ions. So you see we have OH minus aqueous combining with H plus aqueous, giving H2O solid liquid. All right. So this is the basis of a neutralization reaction. Neutralization. We have a base, which is OH minus, combining with an acid that is, donating its proton, H plus. There's our acid, and it gives water. So here's really the crux of it, the most important part of a neutralization reaction. And so what's important here is when the number of moles of OH is equal to the number of moles of H plus, then we've neutralized our solution and we've created only water. All right, so let's do a learning check of thinking about neutralization. Remember, neutralization is an acid plus a base to give water and a salt. So let's write the neutralization reaction for stomach acid, HCl, and Mylanta, which is a drug that contains aluminum hydroxide and magnesium hydroxide. So this is just, to calm upset stomachs, right? So if we kind of look at what's going on here, so stomach acid, here's our acid part of our neutralization reaction. Magnesium hydroxide and aluminum hydroxide are both bases. All right, so we're actually going to write two equations here. So let's just look at the first one. Let's look at the neutralization reaction between HCl and aluminum hydroxide. So neutralization reactions are always HCl, there's our acid, plus our base, so aluminum hydroxide, and we'll say it's aqueous, gives us, we know we're going to form a salt and water. So neutralization reactions are just double displacement reactions. So you just switch partners. So chloride will go with aluminum, hydrogen will go with hydroxide to make water. All right, and so if we look at the charges here, aluminum is 3 plus, and everything else just has like a 1 charge. So H is 1 plus, chloride is -1, hydroxide is -1. So to balance aluminum, my product is going to be aluminum chloride with 3 of them, because we need 3 chlorides to balance 3 plus aluminum. This is aqueous if you look at the solubility table. And then finally, H combining with OH gives us water. And that's always a liquid within neutralization reactions. Now we need to make sure that it's balanced. So I see I need 3 chlorides, all right, on our reactant side, so I'm going to put 3 there. And now this is balanced. So there's 3 chlorides, 1 aluminum. There's 3 hydrogens combining with 3 OHs to give, oh, no, that's not balanced. Come on. To give 3 waters. Because you can essentially think of water as HOH. So since we are combining 3 OHs with 3 hydrogens or hydrogen cations, then you will get 3 waters total. All right, so that's the neutralization reaction for the first substance. Now let's do it for the second substance. All right, and so it's literally exactly the same, except a different base. All right, and so we're going to do, swapping partners again. So magnesium is going to go with chloride, hydrogen is going to go with hydroxide to form water. Magnesium has a 2 plus charge. So when we combine magnesium and chloride, our product is going to be magnesium chloride with 2 chlorides, so it's balanced. And our other product is water. Let's make sure that this is balanced. I see that there's 2 chlorides here, so I'm going to put a 2 in front of HCl. All right, and so 1 magnesium, 2 chlorides. There are 2 hydroxides combining with 2 protons, so we're making 2 waters here. Right? So there is our balanced reaction for the neutralizations of aluminum hydroxide and magnesium hydroxide. All right, so now that we have balanced equations, now we can do stoichiometry and things to calculate problems within titration problems, which is what I want to get to next. So the important thing with titrations is that we need to have a balanced equation in order to use stoichiometry. So here's another example of a different neutralization reaction between sulfuric acid and sodium hydroxide. So it's already balanced here. So sulfuric is our H2SO4 is our acid, sodium hydroxide is our base. So you actually see here that there are 2 protons on our acid. So you essentially need 2 sodium hydroxides in order to neutralize it. 2 moles of sodium hydroxide are required to neutralize 1 mole of sulfuric acid. While if we look back over here, so if we look at magnesium hydroxide, there are 2 hydroxides here. So you need 2 moles of acid in order to neutralize 1 mole of magnesium hydroxide. Or if we look at aluminum hydroxide here, there are 3 hydroxides that you need to neutralize. So we need 3 moles of HCl to neutralize 1 mole of aluminum hydroxide. So this example is kind of the same, except now we have 2 protons that we need to neutralize with base. So the important thing here is that at neutralization, moles of hydronium must equal moles of hydroxide. So we need to have the correct coefficients in our balanced equation in order to use stoichiometry. So let's use these skills in a titration problem. So we have a 10.000 milliliter sample of sulfuric acid, and it's titrated with 16.51 milliliters of 0.125 molarity sodium hydroxide. What is the molarity of sulfuric acid? So remember, molarity is equal to moles over liters. All right. So we know the question tells us how much sulfuric acid that we start with. It's 10 milliliters. So just convert that to liters, right? It's 0.01000 liters. So we know the liter part of the molarity of sulfuric acid. We need to figure out how many moles of sulfuric acid are there. But because we know how much sodium hydroxide we used and we have the balanced equation, it's literally it's just a solution chemistry question, but it's between acids and bases. So really, we're learning nothing new here, but we're just kind of applying it in a different way. So we need to figure out moles of sulfuric acid, right? And so to do that, we actually want to start with the thing that we're titrating with. So in this case, sodium hydroxide. So I'm going to start with sodium hydroxide because that's our known value. So I'm going to start with the volume that we started with, because you always start with, you never start with molarity. You always start with like moles or liters or volume or something. So if we start with 16.51 milliliters of our sodium hydroxide, let's convert that to liters real quick. 1 liter. So now we have liters of sodium hydroxide. We can rewrite that molarity as 0.1251 moles of sodium hydroxide is equal to 1 liter of solution. So we can use that volume and the molarity to figure out, okay, how many moles of sodium hydroxide did we use? So let's do that. So 1 liter is 0.1251 moles of sodium hydroxide. All right. And so, I mean, also you can just use the equation here. So now that we're in moles of sodium hydroxide, we can convert that to moles of sulfuric acid. So 2 moles of sodium hydroxide is required to neutralize 1 mole of sulfuric acid, H2SO4. Essentially what we're saying here is that moles of hydroxide must equal our moles of hydronium, or H plus, coming from sulfuric acid. This is essentially what we're saying right here, but we're just using stoichiometry, essentially. So now we have moles of sulfuric acid, all right, and you can just calculate that. So you get 0.001033 moles of H2SO4. So that's how many moles of sulfuric acid are there. So if we want to calculate molarity, we do moles of sulfuric over the volume or liters of sulfuric. And we have both those numbers. So moles is equal to 0.001033 moles. And the volume that we started with was 10 milliliters or 0.01000 liters. And so if we look at our sig figs here, there's 4 sig figs in each here. See, there's 4 sig figs. We need 4 sig figs. Our volume over here is 4 sig figs. So our answer should have 4 sig figs. And so my answer is 0.1033 molarity of H2SO4. All right. So really, this titration question is nothing new. It's essentially just another solution chemistry problem using molarities and volumes and a balanced equation to understand stoichiometry. But the important thing here to understand in acid-base titrations is that the moles of hydroxide must equal the moles of H plus at our neutralization point.